we have this idea of an antiderivative, and to calculate, quote unquote, calculate antiderivatives or indefinite integrals, essentially we've just been guessing. But since an antiderivative is the opposite of a derivative, any derivative rule that we have, we can turn into an antiderivative rule. So let's look at examples of what that would look like. So for example, here's the power rule for differentiation. This is saying that the derivative of x to the n is nx to the n minus 1, but we can turn that around and rephrase this as a statement about antiderivatives. To rephrase this in terms of antiderivatives, what it's telling us is that x to the n is an antiderivative for nx to the n minus 1. Right? In other words, right, we have these symbols we can use to express the idea of an antiderivative or an indefinite integral. So the antiderivative of n times x to the n minus 1 is x to the n. Although when we rephrase things as antiderivative rules, we have to remember that we have to add a constant here, right? Because always there's this constant that could be anything. Usually when we rephrase the power rule as an antiderivative rule, usually we will rearrange the powers so we'll increase everywhere n shows up, we'll actually add 1 to it, just so that in the thing in the left we have x to the n. So that gives us antiderivative of n plus 1 x to the n is x to the n plus 1. And then also, in this case, it's nice to have just x to the n on the left-hand side, because usually in examples, right, you don't have extra constants sitting around all the time. So really what you're interested in is what is the antiderivative of x to the n. And we can find that by dividing both sides by n plus 1. And it's not really clear that that is sort of an okay thing to do. But remember, we can always check that this antiderivative rule that we're developing is correct just by checking it. We can take the derivative of the right-hand side and see if we get x to the n. Notice that I'm not dividing this constant by n plus 1. And the reason is an arbitrary constant divided by n plus 1 is still an arbitrary constant. So this c in my second line is actually a different constant than the one up here, but they're both arbitrary. So, and once we have our new constant, we're never going to use the old one again, so we might as well just rename c over n plus 1, rename it c. All right, so here's the power rule for antiderivatives. And if you do check it by taking the derivative of the right-hand side, you do get x to the n. So this does check out. Well, we can do this for any derivative rule. For example, the constant multiple rule. Here's the constant multiple rule as a derivative rule. If we rewrite this as an antiderivative rule, it looks like, well, the antiderivative of a constant times a function is the constant times the antiderivative of the function. And again, you can check that this is correct just by taking the derivative of both sides. If you take the derivative on the left, so if you take the derivative on the left, the derivative of an antiderivative, well, the antiderivative undoes the derivative, but then the derivative redoes the derivative, and so you're back where you started with a f of x. And on the right-hand side, if you take a derivative, you get, right, first you have to use the constant multiple rule for derivatives to move a outside, and then you have a times the derivative of the antiderivative of f of x dx, but the derivative of the antiderivative of f is just f. And you can see that these are equal. So this checks out. We can also translate the sum or difference rule into an antiderivative rule. So it looks like antiderivative of f of x plus g of x dx is equal to the antiderivative of f of x plus the antiderivative of g of x. Pretty much what you would expect. Also, if you have a difference inside of your antiderivative, that turns into a difference on the outside as well. You might wonder, why is there no plus c on the right-hand side of these? And there's no plus c because there's still an antiderivative in both of these. And these antiderivatives are sort of hiding the plus c. If you actually calculated, if you had some example where you had particular functions f and g, and you were calculating these antiderivatives, then when you actually wrote out the formula for the antiderivatives, that's when you'd write the plus c. So the antiderivative is really hiding the plus c part. Of course, we have many more derivative rules than just these, but each of them gives you an antiderivative rule. So, for example, derivative of sine is cosine. That means the antiderivative of cosine is sine plus a constant, right? The derivative of e to the x is e to the x. That means the antiderivative of e to the x is e to the x plus a constant. And this one we used before. Derivative of natural log of x is 1 over x, and so the antiderivative of 1 over x is natural log x. Although, right, this is true only when x is positive. If you want it to be true for other x values, we've seen that you need an absolute value here. Now that we sort of recognize that every derivative rule gives us an antiderivative rule, we can maybe work out some more complicated antiderivatives. So let's find the general antiderivative of each of these. When I say general antiderivative, what I mean is we want a plus c on the end. There's no specific antiderivative that we're looking for, and so we should write down all of the possible antiderivatives we can find. All right. So for this one, x squared minus 3x plus 1, right, we're going to find an antiderivative of this. We can use, right, the sum and difference rule for antiderivatives says we can just find the antiderivative of each piece separately. And for each of these pieces, we can just use the power rule for antiderivatives. So the power rule for antiderivatives says that the antiderivative of x squared, we increase the power by 1, and then we divide by the new power, like this. Okay, and then minus. Now the constant multiple rule says we can just write down that 3 and then use the power rule on this x to the first term. So antiderivative of x to the first, you increase the power 1, so now it's x squared, and you divide by the new power. And then the antiderivative of 1, well, that's x. And then don't forget the plus a constant. All right, how about this example? Secant x tangent x plus sine x. So there's a trap here. It's tempting, so the sum rule says we can take the antiderivative of secant x times tangent x and then add that to the antiderivative for sine x. And it's tempting to say, well, this should be the antiderivative of secant x times the antiderivative of tangent x. But is that true? Why would that be true? Do we know that that's true? Did we come up with this antiderivative rule from some derivative rule? No, we didn't. What derivative rule would this come from? Well, it would have to come from the product rule, but this doesn't look like the product rule, right? The product rule for derivatives is more complicated than this. So the product rule for antiderivatives is also more complicated than this, and we won't talk about it at this point, but I just wanted to warn you that if you have a product inside of an antiderivative, you cannot just take the antiderivative of each piece separately. That just doesn't work. It gives you wrong answers. And you can check that it gives you wrong answers, right? If you tried to take the antiderivative of x times x, by taking the antiderivative of each piece, you'd get 1/2 x squared times 1/2 x squared. This is 1 over 4x to the 4th, but the derivative of 1 over 4x to the 4th is x cubed. It's not x squared. So you can't split up antiderivatives on a product like this. So for this example, we need some other way to come up with an antiderivative for secant times tangent. So we're looking for a function whose derivative is secant times tangent. But when you say it that way, we actually know a function whose derivative is secant times tangent. It's secant. So the antiderivative of this piece is just secant. Now we need to add the antiderivative of sine. Well, the antiderivative of sine is negative cosine, not positive cosine, careful. But then, right, so here's an antiderivative for the function we started with. To get the rest of them, we have to add a constant. Okay, so our final answer is secant x minus cosine x plus a constant. All right, last example, let's find an antiderivative for 2 over 1 plus x squared. Well, the constant multiple rule says that, I guess first we can rewrite this fraction as 2 times 1 over 1 plus x squared. And then the constant multiple rule for antiderivatives says that we can just move this 2 outside of the antiderivative. So we get 2 times the antiderivative of 1 over 1 plus x squared. Now we're looking for a function whose derivative is 1 over 1 plus x squared, but we know a function whose derivative is 1 over 1 plus x squared, and that's arctangent, or inverse tangent. All right, and now that we found one antiderivative, we can just add an arbitrary constant to get the rest of them.